Welcome back, everyone, to another deep dive. This time, we're going to be talking about cosmology, but not just like, the science of the universe. We're going deeper. We're going to talk about the fights, about how we should even study the universe.
Oh, it's a really interesting period, yeah. A lot of really strong personalities, a lot of really interesting science. We're going to be focusing mostly on stuff that happened in the 1930s and 40s, using as our sort of jumping off point an entry from the Stanford Encyclopedia of Philosophy. It's called Cosmology, Methodological Debates in the 1930s and 1940s.
So to set the stage here, think about scientists getting so worked up about the right way to do science that they end up kind of throwing shade at each other in, like, Nature magazine. That's basically what happened in cosmology.
To really, I think, get a handle on these debates, you really need to understand what the situation was like at the time. So, in the early 20th century, Einstein's theory of general relativity comes along, and it totally changes the way we understand gravity. Like, we went from thinking about gravity as a force to seeing it as how space-time gets curved. It's a tricky concept. I think an analogy people use sometimes is to imagine like a bowling ball on a trampoline. That's kind of how massive objects warp the fabric of space and time.
Okay, I think I can kind of picture that. So how did this new view of gravity, that gravity is how space-time gets curved, how did that lead to the models of the universe that we use today?
Right. So in 1917, Einstein and another big name in astronomy, De Sitter, both came up with models of the universe based on this idea of general relativity. The problem was that both of these models had like some pretty big issues. Einstein's universe was like way too packed with matter. It was too dense. And De Sitter's universe, on the other hand, it was practically empty. And neither one of them really matched up with what astronomers were actually seeing when they looked out into space.
So it was kind of like a puzzle with missing pieces, but they just didn't have all the pieces yet.
Yeah, exactly. And then in 1929, Edwin Hubble, he makes this incredible discovery. He notices something called redshift in the light coming from distant galaxies. And what that redshift implied was that those galaxies were moving away from us. The universe was actually expanding.
Wow, so that must have, like just totally flipped the field of cosmology on its head.
Yeah, absolutely. Yeah, totally changed things. So this discovery led to like a ton of new models, all trying to explain this expansion. And the one that sort of came out on top was one by Georges Lemaitre. He was a Belgian astronomer. His model was basically an expanding universe, and he actually used the analogy of a balloon to explain it. Like, imagine you've got a balloon with dots on it representing galaxies, and as you inflate the balloon, those dots move farther and farther apart. It's the same way with galaxies in our universe.
Okay, that makes sense. I like that.
And this was really like the birth of what we call relativistic cosmology, right? Building on that idea of relativity.
But this is where the fun starts. This is where the philosophical battle begins, right? Enter E.A. Milne, who I guess just decides to kind of rock the boat only 9 months after everybody seemed happy with Lemaitre's model. What was going on there?
Yeah, so Milne was an astrophysicist at Oxford, and he brought with him these two pretty radical ideas that really challenged how people were thinking about cosmology at the time. His first idea was something called operationalism.
Okay, got to be honest, that word sounds a little bit intimidating. What exactly did he mean by that?
Well, it's simpler than it sounds. What Milne believed was that we should only really consider something like scientifically real if we can directly observe it. And so this challenged things like using ideas like curved space or even expanding space, which were really central to, the relativistic cosmology at the time.
So it's kind of like he was saying, look, if you can't measure it, it's not real, at least not for science.
Yeah, pretty much. And his second radical idea was this thing called hypothetico-deductivism.
Okay, that sounds like a mouthful.
Yeah, it's a long one. Basically, it means you start with a bold hypothesis, and then you use logic to figure out what observations should logically follow from that hypothesis. And this really challenged the way of doing science that was popular at the time, which was mostly inductive empiricism, where you gather a bunch of data and then you try to build theories from it.
So Milne was going for a more theory-first kind of approach, while like a lot of other scientists were more data first.
Exactly. And this sparked this huge controversy, not just about, the equations or the specific models, but about like what science even is.
I bet that got people fired up. So Milne, he didn't just criticize, right? He actually came up with his own model, kinematic relativity.
Yeah.
What was that all about?
Right. So kinematic relativity, it leaned heavily on Einstein's theory of special relativity, but it kind of went in a different direction with it. Milne's big idea was that all measurements, like ultimately they all boil down to timing signals between different observers.
Okay.
And he was talking about using things like light signals, for instance, to measure time.
Yeah.
And he even argued that you could understand things like space and velocity through these time measurements.
So it was all about clocks and signals. I mean, that sounds pretty abstract. But,
Perfect.
but, but I'm guessing there's some real world stuff that comes out of that, right?
Yeah, absolutely. Actually, another prominent cosmologist, Hermann Bondi, he later said that Milne's idea led straight away to the radar speed gun.
Whoa. I never would have guessed that.
Yeah.
Okay, so Milne, he basically throws down this philosophical gauntlet, and the reactions, I'm guessing they were pretty mixed.
Yeah, that's a good way to put it. So Eddington, who was a big defender of relativistic cosmology, he really went on the offensive. He argued that these theoretical concepts, like curved spacetime, were really important for understanding the universe, and that Milne's operationalism was, way too limiting. It was too restrictive.
So real clash of the titans here.
Yeah, and there were a lot of people who agreed with Eddington. One guy named Dingle, for example, he was a strong believer in empiricism, the idea that science should be based on observation and induction, that kind of bottom-up approach. And he really thought that Milne's methods were, like, totally unscientific.
So it was kind of team empiricism versus team rationalism, I guess. What about other viewpoints? Were there other people who had something to say?
Yeah, for sure. There was a guy named Robertson who he was skeptical of Milne at first, but then later on he actually started to use some of Milne's operationalist ideas, which is pretty interesting. And then there was some younger cosmologists, people like McVitie and McCrae, each of them with their own take on Milne's work. McVitie, he thought that Milne's physics was really interesting, but he wasn't totally convinced by his philosophical ideas. And then McCrae, he saw a lot of potential in what Milne was doing, especially for explaining how the universe expands, which was still a big puzzle for the relativistic cosmology people at the time.
Okay, so we've got these clashing personalities, we've got scientific disagreements, and then we've got these like deep philosophical divides. This is getting pretty interesting.
Oh, yeah.
So how did Milne deal with all of this pushback, all of this criticism?
Well, Milne, he just kept refining his arguments. He gave lectures, he wrote papers, and he really emphasized how important it was to start with clearly defined concepts and then use deductive logic to build your theories. And he was really inspired by mathematicians like Whitehead and Russell, who were big believers in the power of like these systems with axioms, these really rigorous ways of building theories.
It's really interesting to see that it wasn't just about like which theory was the right one, but also like how do we even define scientific knowledge? How do we know what's real in science? How should we build theories in the first place? Those are some pretty big questions.
Absolutely, absolutely. And, as Milne kept, developing his arguments, this clash with Eddington, it actually like got even more intense.
Oh, I bet.
Eddington was totally convinced that these concepts in relativistic cosmology, like curved space-time, that those things were physically real, And Milne, he kept saying, no, the only things that should be considered real for science are things that we can actually directly observe,
It's a real philosophical battle royale at this point, it sounds like.
Yeah.
And I have a feeling things are about to get even more heated.
Oh, yeah. Just wait until we get to Dingle's article in Nature.
Oh, boy.
It's a doozy.
That's what we call a cliffhanger. We'll be back soon to unpack the next stage of this cosmological showdown, so don't go anywhere.
Welcome back to our deep dive into the philosophical battles that really shaped cosmology. Last time we left off with E.A. Milne kind of stirring up the scientific community with this really, really bold approach to cosmology, that focused a lot on deduction.
Yeah, it was a real clash of the titans. We had some big personalities and even bigger opinions flying around. But as we're going to see, Milne's impact went way beyond just, starting debates.
Yeah, that's right. So even though Milne's specific model of the universe, kinematic relativity, even though that didn't really become the standard model, his philosophical approach, it really had this lasting impact. It really made cosmologists think carefully about, how science should actually be done, what the assumptions were.
It's fascinating how somebody's ideas can have such a broad reach, even if their specific theory, doesn't ultimately get adopted. So what happened next in all this?
Well, so in 1939, two pretty prominent scientists, McVitie and Temple, they were tasked with reviewing the state of cosmology for a joint meeting of the Royal Astronomical Society and the Physical Society of London. And their reports, which came out shortly after this meeting, they offer this really, really interesting snapshot of where the field was at the time.
Okay, so how did they present Milne's work? Was he still seen as like this radical outsider at this point?
Not at all. Actually, both McVitie and Temple, they presented both kinematic relativity and relativistic cosmology as equally valid ways to account for all the observations that were being made about the universe at the time. So it seems like Milne's ideas, they were really starting to gain some serious traction.
Wow. So Milne went from being this like controversial figure to being, kind of recognized as a serious contender in this whole cosmological arena. That's quite a shift in what, just a few years.
It really is, yeah. And what's even more remarkable is that Temple, in his report, he specifically praised Milne's operationalist and axiomatic approach. He actually highlighted the elegance and simplicity of Milne's method of correlating measurements between observers using just, light signals.
Okay, so Milne's clocks and signals idea, which got so much pushback early on, was now being recognized as like this powerful way of understanding the universe.
Exactly, exactly. And, this wasn't just like some offhand comment. Temple's report was widely considered to be like the definitive overview of cosmological theory at the time. It was like the successor to this very influential 1933 paper on relativistic cosmology by Robertson. You could even say that Milne's methods, in a sense, they'd kind of triumphed.
That's incredible. It's amazing how quickly things can change, in science.
Yeah.
So what happened to Milne after this? Did he keep being this major player in these cosmology debates?
Well, so Milne, he stayed active in the field, yeah, but his own like personal contributions, to the more philosophical side of cosmology, they kind of started to wind down, and his cosmological model, kinematic relativity, it didn't really gain much more momentum.
It seems like even though his methods were getting more influential, his specific theory, it didn't quite catch on. Why do you think that was? Was it just like too radical for most physicists at the time?
Yeah, it's hard to say for sure. I think there were probably a few reasons. Even though a lot of people were starting to accept Milne's philosophical approach, a lot of physicists, they still just preferred the way you do math with general relativity. It offered this really powerful and really elegant way to describe, gravity and the universe. And I think a lot of people were just kind of reluctant to abandon that.
So it was partly just like a matter of scientific taste, kind of like preferring one set of tools over another.
Yeah, I think that's part of it. And also kinematic relativity, it was arguably more complex, a little less intuitive than relativistic cosmology. Milne's focus on timing signals and his way of defining space and time, it was pretty conceptually challenging, even for physicists back then.
So it sounds like it was maybe just a little bit too out there for most people, even if some of his ideas were starting to take root. But you mentioned, scientific taste, and it makes me think about how those philosophical preferences can really shape, where science goes, what questions get asked.
Oh, absolutely. Milne's like his insistence on starting with these really clearly defined concepts and then using deductive logic to build a theory, it really went against the grain of, this inductive empiricism that was so popular at the time. He really made cosmologists, wrestle with this question of what makes a good scientific theory. And that question, it's as much a philosophical question as it is a scientific one.
And as Milne's story shows, challenging the status quo, even if it leads to like a lot of controversy, it can be really, really productive in the long run. It can push the boundaries of scientific thought and open up, whole new ways of looking at things. But even though his own cosmological model, didn't win out in the end, his influence, it didn't stop there,
Yeah.
right?
No, not at all. So in 1942, Milne was given this pretty prestigious award, the James Scott Prize for natural philosophy. It was really an acknowledgement of his contributions to the field. And then the next year, he was elected president of the Royal Astronomical Society, which was, like the ultimate honor for a British astronomer.
That's quite a turnaround. The
Hmm.
guy who was once seen as this like radical outsider was now, the head of the very institution that was initially so skeptical of his ideas.
Yeah, it's really remarkable, and I think it just speaks to the power of his ideas, to his commitment to these philosophical principles that he had. And even though later on he did admit that he'd kind of modified some of his earlier views, he never wavered in his belief that deduction and the search for these elegant axiomatic theories are incredibly important.
And as we'll see, his legacy, it kind of lived on through the work of another really interesting cosmologist, Herman Bondi, and the development of the steady state theory. Are you
Yeah.
ready to jump into that?
Absolutely. Yeah, it's a fascinating story, really. It's an example of how Milne's ideas, even though they might have seemed unorthodox at the time, they found this new life in this really radical cosmological model.
Welcome back to the deep dive. We've been, tracing the story of E.A. Milne, this astrophysicist who really kind of shook things up in cosmology, even though his own model of the universe, kinematic relativity, didn't become like his philosophical approach had this ripple effect, and that ripple, it actually led to something even more radical, I think.
You're talking about the steady state theory?
Exactly. The steady state theory. So this was proposed back in 1948 by Herman Bondi, along with Thomas Gold and Fred Hoyle.
Oh yeah, this is the theory that basically said the universe has no beginning and no end. It was a really, really different idea from the Big Bang theory, which was kind of becoming the dominant theory. The Big Bang theory said the universe started from this single point, and it's been evolving ever since. But the steady state universe, it was eternal, it was unchanging, it always looked the same no matter, where you looked or when you looked.
It's kind of a mind-blowing concept when you really think about it. What was it that led Bondi to this really radical idea?
Well, this is where I think Milne's influence really comes in. Bondi, he was so impressed by Milne's his deductive approach to cosmology. Starting with this fundamental principle and then just working out all the logical consequences. Bondi thought this was a much better approach than what he called the extrapolating approach, which was all about observation and generalization.
So Bondi was basically Team Milne in this whole cosmology debate.
Oh, yeah, very much so. He really admired how rigorous Milne was, how elegant his arguments were. He even praised Milne's operationalist definition of distance, that very idea that got so much criticism early on.
Wow, it's amazing how Milne's ideas, the things that were controversial at first, were now being seen as like the foundation for this whole new cosmological model.
Yeah.
So how exactly how did he use Milne's thinking to come up with the steady state theory?
Right. So Bondi, he started with what he called the perfect cosmological principle, or the PCP. It was basically like the souped-up version of Milne's cosmological principle. So Milne's principle said that every observer in the universe should have the same world picture at any given time.
Okay, so no matter where you are in the universe, you'd see the same basic large-scale structure.
Right, exactly. But Milne's principle, it still allowed for, the universe to change over time. But Bondi's PCP, it went even further than that. It said the universe should look the same, not only from any location, but also at any time.
So no beginning, no end. Just a universe that always was and always will be. A universe in a steady state, like the name says.
Precisely. But Bondi's philosophical influences, they weren't limited to Milne. He was also really influenced by the work of the philosopher Karl Popper.
Ah, Karl Popper, the champion of falsifiability in science. How did that fit into all of this?
Well, Popper, he argued that for a theory to be, truly scientific, it had to be testable. It had to make predictions that could, potentially be proven wrong by observations. And Bondi, he really took this to heart. He wanted his steady-state theory to be vulnerable, in a sense. He wanted it to be disprovable if the evidence didn't support it.
That's a pretty bold move for a scientist. It seems like most scientists are trying to prove their theories right, not wrong.
Yeah, but that was the really cool thing about Bondi's approach. He saw falsifiability as a strength, not a weakness. It gave his theory this kind of scientific integrity, this willingness to be judged by the evidence.
So Bondi's steady-state theory, it was like this knight in shining armor, ready to, face any challenge, any observation that might come along.
Yeah, that's a great way to put it. And for a while, it really held its own. But like with any scientific theory, the real test is, does it match what we observe?
And that's where the steady-state theory ultimately, met its end. The discovery of the cosmic microwave background radiation back in 1965 by Arno Penzias and Robert Wilson, that changed everything.
Oh, yeah, absolutely. So this radiation, it's like this really faint afterglow of the Big Bang. And this discovery, by the way, it won Penzias and Wilson the Nobel Prize later on. But, this radiation, it was basically the fossil that Bondi had challenged his opponents to find. It was concrete evidence that the universe, you know, it wasn't always the way it is now. It had a beginning, and it's been changing ever since.
So the universe wasn't in a steady state after all. It had this hot, dense beginning, and it's been evolving over time.
Right. And to Bondi's credit, he totally accepted this new evidence. He admitted that the steady state theory, it wasn't a good model anymore. And I think that shows how committed he was to Popper's philosophy of falsifiability. He built a theory that could be, disproven by the right evidence, and when that evidence showed up, he didn't try to cling to it, he let it go.
That's a great lesson for any scientist, and really for anyone, I think.
Mm.
Sometimes letting go of an idea, even if it's an idea that you really like, it's the most intellectually honest thing to do.
I totally agree. So while the steady state theory isn't really considered a good cosmological model anymore, it did leave behind this really important legacy. It pushed the boundaries of scientific thought, it led to a lot of new research, and it forced cosmologists to think about these really fundamental questions about the universe and what it's all about. And it all started with Milne and his challenge to the status quo, his belief that, a deductive approach to cosmology was the way to go.
So as we wrap up our deep dive here into cosmology's philosophical wars, what's the big takeaway? What should our listeners be thinking about?
Well, I think it's a really good reminder that science, it's not static. It's not just this set of facts, set in stone. It's this dynamic process. It's always evolving. It's driven by curiosity and creativity and yeah, sometimes even, a little bit of rebellion. It's about asking big questions. It's about challenging assumptions, and it's about being, honest with yourself, being willing to let go of ideas when the evidence says you should.
And maybe even more importantly, even a theory that turns out to be wrong, it can still be incredibly valuable. It can spark new ideas, it can lead to amazing discoveries, and ultimately can help us understand the universe better, and understand our place in it.
Yeah, very well said. And, who knows, maybe Milne's kinematic relativity, which it's actually seeing a little bit of a comeback these days, maybe it still has some surprises in store for us.
That's the cool thing about science. There's always more to learn, always new mysteries to uncover. Thanks for joining us on this deep dive into the fascinating world of cosmology and all the philosophical battles that shaped it. Until next time, keep those minds curious and those questions coming.